Hey guys, welcome back to another weekly tutoring episode on the best tutoring YouTube channel on YouTube, Chemistry Uncovered. Here at Chemistry Uncovered, our mission is to uncover the mysteries, go under the lens and to uncover the mysteries of chemistry to make them more simplistic, but to also make them more enjoyable for you guys and more collaborative for you guys, right? And so without further ado, the topic we're talking about is quantum chemistry, right? Like the QuantuMania of chemistry, just exploring what quantum chemistry is, the quantum mechanics behind it, the wave particle duality, and the quantum numbers. So throughout this video, I will be talking about the wave particle duality, the quantum mechanics, and the quantum numbers. I remember when I was little, these topics really captivated me because these are kind of on the frontier of scientific discoveries right now. They're so small, they're so atomic in practice that I was just curious on how does this work, right? So I hope you guys have the same exact curiosity. First, wave particle duality, right? Wave particle duality is basically the phenomenon where particles they can exist as both a wave and a particle. For example, in the double slit experiment, when you have light photons that go through two slits in between these three blocks, it creates a ripple effect of waves, and the yellow parts are the ones that are lit up. The white parts are the ones that aren't lit up. The lit up ones have waves that reflect on each other, a constructive interference where the amplitude of the wave is doubled. And for more information about amplitude, go to last week's video, which I go in depth about waves and the amplitude. And in the part where it doesn't light up, that's destructive interference. In other words, the waves, as seen through in this graph, the waves do not reflect on each other, and so they kind of cancel out to a straight line. So this proves the wave function of a wave particle duality. For the particle part of the duality, when you shine a light on a metal, one electron is oxidized, so it's released from the metal, right? And this proves that it's a particle because a particle is the only thing that can cause the electron to be emitted. And electrons are just tiny particles, so an electron has both wave qualities and particle qualities. Without further ado, quantum numbers, right? Quantum numbers, so why are they important? You guys may be asking. Well, first of all, it determines the location and energy of electrons. Oftentimes, I'm like, oh, okay, the electron is in energy level 2, energy level 3. But why? Using chemistry, how do I explain that? How do we explain that, right? Also, quantum numbers describes different atomic orbitals. Essentially, in each atomic orbital, in each subshell, there's two electrons, and it describes the different type of atomic orbitals in its respective subshells and energy levels. So what are orbitals, you guys may be asking? You guys may have heard me talk about orbitals, or your teacher or other chemistry tutors talk about orbitals, but what are they specifically? Orbitals is the region of probability where electrons can be found. So it's not a finite determinant where electrons are found there. It's a probability where it's safe to assume the electrons can be found there. And also it's important to note that every orbital holds two electrons. And so the first quantum number we're going to talk about is the principal quantum number. Essentially, it's denoted by the variable n, and n equals 1, 2, 3, 4, etc., all the way to infinity, represents the energy level of the electron. So if you look at this Bohr model on the bottom of the graph, the first energy level is the ground state energy level, and obviously as the electron gets excited, it goes to the second energy level, third energy level, and fourth energy level. The second quantum number is the angular momentum quantum number. This is denoted by the variable L. L is essentially n minus 1. So if you have one energy level, then your L value is 0. If you have two energy levels, your L value is 0 and 1. If you have three, your L value is 0, 1, 2. This describes the shape of the orbital. Now, I won't go into depth about the shape of the orbital, but if you look at this graph right here, the S orbital, which only has one orbital, so it's L equals 0, that value. The S, it's a circle, and so this is the probability where the electron can be found in the circle, and so on for P, D, F, right? For magnetic quantum number, it's denoted by the variable ML, which is basically, it goes from the whole numbers, the integers, from negative L to positive L. So if we go back to this angular momentum quantum number, right? If we had a value of L equals 2, then the magnetic quantum number would be -2, -1, 0, 1, 2. If we look at this example right here, we have L equals 0 and 1 and N equals 2. The total energy levels is 4, but inside the total energy levels for the first orbital for 0, there's 1 energy level, and for the first subshell 0, there's 1 energy level, and for the L equals 1, there's 3 orbitals. Sorry, I wrote energy levels there, but it's in reality it's orbitals. So there's 3 orbitals inside the L equals 1. So yeah, so basically the magnetic quantum number determines the amount of orbitals for a given energy level, right? So if we have N equals 2, in total there's 4 orbitals. So I wrote 4 energy levels, it's actually orbitals. And then the last but not least, the last quantum number we have is the spin quantum number, right? The spin quantum number is denoted by ms, which is either a positive 1/2 magnetic spin or negative 1/2 magnetic spin. It determines the spin of the electron inside the orbital inside the subshell. And so basically, essentially, what the Pauli exclusion principle states is that both electrons in the same orbital have a different magnetic spin. So if you have 2 electrons like occupying the same orbital, which by the way, 2, if you recall, is the maximum amount of electrons you can have in an orbital, they both have to have different magnetic spins. So one electron has a positive magnetic spin, one has a negative magnetic spin. And by the way, magnetic spin, the positive negative, isn't denoting the charge of the electron, okay? That's a very important distinction. I know that a lot of you guys may be confused about. This is magnetic spin in the quantum level, not the charge of the electron. So coming up next week, we're gonna implement the quantum knowledge we learned in this video, the quantum numbers, the quantum mechanics, the wave particle duality, and we're gonna implement that into a periodic table. Find how we use it to determine the electron configuration of elements such as sodium, magnesium, boron, carbon. And we're also going to use the Aufbau principle to determine how to write electron configurations. So thank you so much for watching, guys, and go outside, enjoy nature, and more than anything, make the world a better place, make the nature around us a better place. The nature is such a beautiful place, and just, be grateful for it and help other people around you. Just do your best to make the world a better place. Also, on top of making the world a better place, make sure to subscribe to our YouTube channel. We are on the road to 1,000 subscribers over the summer, and so please support the movement and comment down below if you want to see Physics Uncovered, where we uncover the mysteries of physics. So if you want to see that, comment down below if you want to see that or not. And thank you so much for watching. Subscribe, turn on your post notification bell. This has been Chemistry Uncovered. Thank you so much for watching. Peace out.